morning. Stefania Costantini, I work at the University of L'Aquila, which means the eagle from which our logo. This work stems from a couple of projects in which my group is starting to participate. The first one is this one. This is a cyber physical system where you have a distributed environment with many knowledge sources, for instance, diagnostic databases, treatment databases, many things about medicine, about patients' care, and so on and so forth. Then you have patients. I just represent one. Patients will have a number of sensors, wearable devices, and so on and so forth, or machines, I don't know, where they can put their finger and measure the sugar and so on. And each patient is in charge of an agent. This agent will have to monitor the patient conditions and to monitor the patient taking his medicines at the right time and so on and so forth. In normal circumstances, the agent operates locally, but assume that the patient shows some values which are different from usual, out of range, or some strange symptoms. At first, the agent will try to manage by itself. For instance, to resort to a treatment databases to rearrange the quantity of medicine, okay? And so, to manage things on itself, it will have to find and exploit a number of knowledge sources. Clearly, if the situation comes out of control, the agent will resort again within this system, because part of these say components will be the health system, medical doctors, the family doctor, and so on and so on, will resort to help by humans and maybe to calling an ambulance, an helicopter, whatever can. Now the point is how to build the system engine, okay, so as to retrieve and integrate heterogeneous multiple sources of knowledge. This is the point of this work. Another related project has started because I have a PhD student who has just finished, but happens to be a high officer of the Italian police. He came to make the PhD while walking because he wanted to apply artificial intelligence in his field. This is digital forensics, or better, digital investigation, okay, in which you exploit digital data or artificial intelligence in general to solve pieces of an investigation. And then we have very promising results in the PhD thesis for the various pieces, okay? Alibi verification, construction of scenarios, a lot of things, okay? But how to put things together, okay? The various pieces of the investigation according to, in this case, legal databases, law, past cases, and so on and so forth. And again, the point is how to build this system engine. Here we are starting, okay, no. Here we are starting, just starting. Here, as I said, we have several implementing pieces that we would like to join together. And in a decision support system for lawyers, for judges, for investigators, and so on and so forth. Now, a very nice way of modeling the system engine in a logical way, but in a rule-based way, is the approach of multi-context systems which was proposed initially by Giunchilli and Serafini, and then actualized, let's say, extended and made more solid by Brecht, Tyler, and others, which this approach explicitly wants to integrate heterogeneous knowledge bases. How do, in first order logic, okay, without resorting to modal logic, circumscription, and other things that are nice but not computationally affordable, because such systems are supposed to work real time. Moreover, an issue that I am considering is that these systems are open in the sense that these knowledge bases in the approach are called contexts, okay, for short. New contexts can join and leave the system, okay, or several contexts may have the same role, which is I can have several services of the same kind, several databases providing the same data, and an agent may even prefer one rather than the other one. There will be a timing in the sense that in reality knowledge sources may ubiquitate, may answer but also don't answer, or don't answer in a timely way. Okay. So there are a number of issues which have to be investigated. In fact, why the approach is rule-based? Because in the multi-context system approach, the various contexts communicate via these bridge rules, which are very similar to data law rules, okay, or to rules in logic programming negation, in the sense that this must be true and this must be false, but in which sense? Each CI here is a context, one of these external knowledge sources, and for S, this rule will itself occur in a context, okay? So, the conclusion will be added to the receiving context if, indeed, these are entailed by the relative context, and these are not entailed by this other context. The assumption is that all contexts are based on logic. This is, and each one on its own logic, because they are heterogeneous. Is this such a strong assumption? But yes and no, because even relational databases are logic, okay? Even a text file can be wrapped, okay, to act as a logic. So let's assume that each context is based on a logic. These logics are different, but anyway, I can talk about these being entailed and these being not entailed. In this improvement, there is the management function, which is the resulting knowledge is not just added, it is elaborated, maybe by means of complex belief revision of the context knowledge base, and then incorporated. And this is now a hint on the semantics. I have a number of contexts, and so a multi-context system M. I have a data state S, which is a semantics for each knowledge base. So the SIs will be acceptable. There will be a semantic acceptability function for each context, which says, yes, SI is a semantic for me, okay, or not. And so a data state is a set of acceptable data states, partial data states, one for each context. And desirable data states are equilibria, which are those data states which are stable with respect to bridge rule application. What does it mean? I take the bridge rules which are applicable in the data state. Applicable means that the body is true, exactly, okay? The C1 entails P1, C2 entails P2, CM does not entail PM here with respect to this specific data state. So P1 is in S1, P2 is in S2, and so on. Okay, so the body is true here I take the applicable bridge rules, which are those whose body is true. I apply the applicable bridge rule on the knowledge basis on each of the contexts. I apply the management function, which is this thing that I elaborate the result, and what I obtain is exactly a sign. A data state which has this property, after applying bridge rules, I obtain the same data state, is stable with respect to bridge rule application. It's called an equilibrium. Okay, and this is very nice. The point of this approach is that in the original definition it works by magic, in the sense that whenever the body is entailed by the present data state, which is distributed, okay, by magic the conclusion is added to the receiving context in no time. Okay, so this is not true in reality, because here there is, we involve both time and the system dynamics. Okay, so the objective of our work is to take reality into account, but logically, not only at the implementation level. Okay, to improve this logic, this approach, so as to take real circumstances into account. What do we want to do in particular? First, here bridge rules, in the original approach, bridge rules are applied automatically whenever they can be applied. Instead, some particular contexts, for instance agents, may wish to apply bridge rules proactively when they want to, not automatically. And this is a first improvement, that when there are no authors, it means that it's me and others. Okay. Then there is a subsequent work that now I cannot comment because I don't have time. Excludes logical omniscience in context concerning bridge rule application. Then temporal evolution of the knowledge basis, okay? Because another thing, in reality, the knowledge basis will not be the same forever, because they will evolve in time by the knowledge will change, hopefully, moreover, because then again in the original approach bridge rules were considered to be ground, which is not including variables, which is a serious limitation in practical terms. Then, as I said, multiple contexts can have the same role, or anyway I must be able to retrieve a context by means of its role in the system, because I not necessarily know its precise name and location in advance. And then another extension, which is in my opinion very important, it is that I don't even know the role, I know the kind of context that I would like to query. And then my systems always include agents. I will present here some pieces, okay, of this set of extensions. One is the thing of bridge rule grounding, because Brefka and Eiter say it shows some examples with non-ground bridge rules, but very simple example where the grounding is straightforward, and then they say a non-ground bridge rule will stand for the set of its ground distances, but it is not so. When you come to produce these ground distances, things are not as simple as it may seem, because first, I might ground each context bridge rule on its own signature, but this is not good, because we want to exchange knowledge, so we must have value invention in each context. So local grounding must be excluded. grounding on the overall signature of all contexts is unrealistic, first because it would obtain in general an infinite number of bridge rules, or however a huge number of bridge rules, and so how to check applicability? Okay. We have tried many things. A possible procedure is this one. Consider the present context knowledge basis. The one that you have now. And consider a finite grounding of this knowledge basis and take this as an initial data state. And then make this perform a finite bridge rule grounding by instantiating bridge rule over the finite and ground set of terms occurring in this knowledge basis, basically. Okay. Then try recursive applications of bridge rules and see if you reach an equilibrium. This is still a bit theoretical, but then we will find a practical counterpart of this. It is not so simple, not even here. It does not mean that you obtain a finite number of bridge rules or that you obtain a finite equilibrium, because, or an equilibrium in finite time. Because take these two contexts, C1 and C2. C1 has a very simple knowledge base. C1 knows that 0 is a natural number. Okay. C2 instead doesn't know anything at the beginning because the knowledge base is empty, but both contexts know that if you have a natural number, its successor is a natural number. Simple as it is, this can be seen as two very small agents that cooperate in generating the natural number, because for how bridge rules work, context C1 knows that 0 is a natural number, so this bridge rule will be applied, and so this will be added to the knowledge base, and context C2 will know that such of 0 is a natural number. Okay. Then now this other bridge rule can be applied, and so C1 will conclude that such of 0 is a natural number. Now again we go to C3, C1, C2 again. Anyway, from one to the other, they will increase the set of natural number. One will always compute the even, and one will always compute the odd. Now, these two do not do anything very special, but it is to show the process of grounding, because we start, as I said, I take the initial knowledge basis and I take one finite grounding of this knowledge basis to start with. In this case, it's very simple. Okay. Then you apply the bridge rule, and you have a second data state which has been obtained by applying the bridge rule in context C1. Okay, but this is not an equilibrium, because now you can apply the bridge rule in the other context, and so on and so forth. So we have an equilibrium which can be reached, however, in infinite time. Or you can have finite approximations to grade k. Okay. Even with this very simple mechanism, you have you are not limited to a finite number of steps or to a finite number of bridge rules. You can generate infinite bridge rules and have infinite steps. Now we have formal results of this, and in particular we have an extension of a characterization of the grounded equilibrium to grade K, no? That in Brefk-Einlager was presented for ground bridge rules. So we took the formal results for ground bridge rules and extended to non-ground bridge rules under this procedure. The only precondition is that you shouldn't have cyclic bridge rule application, in the sense that that I don't explain, however. They defined this property, this characterization for definite multi-context system with non-negative subgoal. But when you come to practice, you can think of executing bridge rules like prologue rules, left to right. Okay, so for the positive subgoals, they are true if the answer is positive and arrives within a certain time. For the negative ones, they can consider it to be false in two cases. Either if the answer arrives and is negative, or if the answer doesn't arrive within a certain time. And so in practice, we show that this characterization say is for definite multi-context system, but in practice work for any multi-context system under this assumption, practical assumption of negation, and also under another assumption which is important, that the system stays stable during bridge rule execution. Because if one context answers while the second context still has to answer, the knowledge in the first one changes, okay, so things, but this is always true in artificial intelligence systems. Either they are timely enough or they are brittle, okay, So another extension is timed equilibria, in the sense that here it is a very schematic representation. First, each context has an update operator. This update operator can actually be a tuple of operators, because you can have sensory input, messages from agents, user intervention, so you have a number of updates which are possible on a context knowledge base. Given the present knowledge base and the present set of new data and the update operator, you obtain a new knowledge base, and in considering equilibria, you must consider that it must not be that this is equal to this, but that the new data state after the update is stable with respect to bridge rule application, because here in the middle there is the update. So update, bridge rule application, possible stability. The other extension is the directory of the contexts presently participating to the system. This directory can change, and the directory admits queries of the form role at directory, which is in my bridge rule, I don't write context CY, I write context, for instance, student office at Stony Brook, okay, so, and this will give me back via the directory the reference to the right context to query, because it is much more general, and also each context may have associated to its, the context has a logic, a knowledge base, and a set of bridge rules. It can also have a preference criterion with its own definition in order to select the best preferred context in case there are many available with the same value. And clearly also, when a bridge rule is executed, not defined, executed, each of the contexts which are mentioned in the bridge rule must be now reachable from the receiving context, because as the system changes, also some contexts can get disconnected just for network reasons, okay? So, at the moment of the actual application of a bridge rule, the precondition is that all the contexts must be reachable, because otherwise application must be delayed. So you can see all these things are formalized. So my point was going from magic, or a very nice, interesting system, to practical but logically founded applicability of the same kind of systems by means of a number of improvements. So, ongoing work are the ACE agent computational environments, which is a work which has been presented at EMAS this year, and also was rated the best visionary paper. I hope they don't mean I'm going distracted, but anyway, this is again, and these ACE and KACE actually are fractal systems of this kind, where each context can in turn be a multi-context system, to make it easy. Okay, so and I would say that that's that.
Questions?
You're concerned with dealing with potential infiniteness and what's an appropriate equilibrium notion as far as semantics and also mechanism for dealing with that. And that's something that people have dealt a lot with in the context of non-multi-context systems, just a single like well-founded logic program, or some of the things, stable logic programs, answer set programs, rule log, etc., etc. So there's a very important notion that we didn't talk about here, which is leastness. So the idea that it's not just an equilibrium, it's not just that's some kind of stable, fixed point type of character like we talked about with equilibrium, but among such, it's the least one, so that things are grounded in the motivational, the sort of justification sense as well. So I was wondering if that's something that you or others in this multi-context system have looked at.
To the best of my knowledge, we are the first ones to cope, apart from the Barilaro and others, but for relational multi-context systems where everything was finite by definition. I believe we are the first ones to and actually my procedure was reminiscent of the construction of the Disturbance model, But the point is not in itself that it is something bad in generating an infinite number of bridge rules. Is that you have to check for applicability. And checking for applicability or an infinite number of bridge rules, at present I don't know how to do. Because anyway, we are just starting. In a subsequent paper we have a more general method, but this is a topic on which we are just beginning and must be investigated. Exploiting, as you said, what it is known for logic programming locally in single. So I completely agree with your point.
Can you combine your approach with static logic, maybe reasoning about what other agents know, K operator?
Yes, but first consider that some of these contexts can be based on static logic. But globally, at the system level, it would be very, very interesting. And it is a thing that I want to study. Whatever you cannot do is something that I saw presented at the PNMR, which is you join all contexts together and reason via epistemic logic. You cannot do that because contexts usually not only are distributed, but they are not yours, and sometimes you even have to pay a fee to get a query answer. So you can just make the query and not access the contents and then. But anyway, I believe that it is possible to make some epistemic reasoning in the system anyway, and it is a very interesting future direction.
Next talk by Greg Collins on